Hey everybody. In this video I'm going to talk about basic logical operators such as OR and AND. So let's dive right into it. What am I talking about with the OR and AND? Suppose for the sake of argument that this notepad is totally dark and I wanted it to be really light, and then I have to go into the system settings to fix it. Sorry, let me change my theme. Graybird, how about that? Okay. So suppose for the sake of argument we've got, a couple of bits. These are going to be bitwise operations for the most part. In other languages, sometimes we will say logical operator, but actually we're just talking about values rather than bits individually. So these are bitwise operators. Imagine we have like a couple of bits. Remember, the possible values for bits are just, a 0 and a 1, binary. So suppose we have a couple of values. Let's say we have a 0 here and a 1. So if I apply a logical OR to the 0 and the 1, the result is going to be a 1 because either the first bit or the second bit are a 1. You could also expand these operators to have multiple sets of bits, but we're just going to do one set against another set. In this case, each set is just 1 bit long, but we'll do more complicated stuff in a minute. So if I have a 0 and a 1, then the answer there is, well, let me just put OR maybe. The answer is a 1. I'll put OR maybe at the top, just like a OR, to let you know that we're doing ORs here on the top. So if we have a 0 and a 1, the answer is going to be a 1. If we have a 1 and a 0, the answer is going to be a 1. Also, if we have two 1s, which looks like an L over there, I got to work on my penmanship, then the answer is also going to be a 1. So the rule is, if either of the bits in question are a 1, then the answer should be a 1. The only case with an OR that results in a 0 is if both of the bits are 0, because neither the first or the second are actually a 1, right? So this is the basic idea of using an OR operator. And you can also do this with multiple bits at the same time. Like, for example, we could say, let's take a bunch of random bits here. Oh, dude, I really need to work on it's the pressure, dude. The L's are driving me crazy. Okay. Oh my God. Okay, so I do that and then I let go. Okay. I'm just going to put some random bits underneath the first set of random bits. Put like a 0 here and then like a 1 here, maybe. And we'll say that we're going to do a logical OR, just like you might think of doing a, addition or subtraction. We'll just say we're going to OR these two sets of bits. Actually, these are 6 on the top and 6 on the bottom. If I add 2 more, then it'll be a nice little byte for the top and the bottom. So I'm just going to do that, to have 8 bits on the top and 8 bits on the bottom. Okay, so if I just want to logically OR 2 sets of bits, literally I just have to do one pair of bits at a time. So a 1 or 0 is just a 1, a 0 or 1 is a 1, a 1 or 0 is a 1, a 0 or 1 is a 1, and then these 1s, everything is just a 1. Okay, so that was too easy. Maybe if I don't know, maybe if I change one of these 1s to a 0, then we would actually be able to have a 0 somewhere in here. So that's a logical or a bitwise OR operator or operation. So you can kind of use this in various ways. I mean, obviously, if you want to manipulate some bits, this can be pretty useful inside of the machine. But there was kind of an old school way that people did flags with arguments. They would basically say something like this. They would go, in their computer program, they would say, flag A, name it something like turn on the display or enable caching or just like whatever, right? So we'll just have a flag, we'll call it flag A. We could say that that value is equal to a 1, and then maybe flag B, its value is equal to a 2, and then flag C, its value would be a 4, and then we basically just double the value of the flag. And the reason for that, C, D, E, F, I'll just stop with F maybe. Oh wait, that was supposed to be 16 and that's 32. The reason for that is if you double the value of each flag so that every flag's actual value has a power of 2, then you can do a bitwise OR against all of these flags and sort of combine multiple flags. Because if you think about it, if we're talking about binary, if we suppose this is just a regular 8-bit number, then the first bit has a strength of 1. If you've seen my other videos for converting between binary and hex, The second bit has a strength of 2. The next bit has a strength of 4, and then 8, and then 16, and then 32, and 64, and then 128. And so if you look at the flags, 1, 2, 4, 8, 16, 32, they map to only one bit. It's not going to be some kind of random pattern for these numbers. It's literally going to be flag A is going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. And then flag B is going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. And flag D is going to look like this. Whoops, let me make that green. Still getting used to this. Oh, sorry. C is the next one. 1, 2, 3, 4, 5, 6, 7, 8. Can you see the pattern here? Let me just do D and be done with it at this point. 1, 2, 3, 4, 5, 6, 7, 8. So because we're increasing the value of the flags by powers of 2, or by a power of 2, they'll always correspond to just one bit, which means if you apply a logical OR operation, you can represent a bunch of different flags with just one number. Think about this. What if I wanted to have, oh, I don't know. Let me erase this. What if I wanted to have some, let's say I wanted flag A and flag D and flag F, just for the sake of argument. Dang, this pen. It's actually my fault completely, but I need to practice. F. Okay. A and D and F. So that would basically be, 1, 2, 3, 4, 5, 6, 7, 8, and then D would be the 8. So a 1, 0, 0, 0 there, and then a bunch of zeros elsewhere. And then the F would be 32. So that's a 0, 0, 1, 0, 0, 1, and then a bunch of zeros. So if we did an OR between all of those, then the OR is just basically 0, 0, 1, 0, 1, 0, 0, 1. And if you convert that from binary to decimal, what is that? That's a 1, 2, 4, 8 plus 8 plus 1, 2, 4, 8, and then a 32. So 41. So literally, you can just write down the number 41, and if the programmer is smart enough to, parse all the bits and everything, then they'll know that you have flags A and D and F set. That's not necessarily something that all the modern programs do anymore. It was much more popular in the olden days, but I think some people still kind of do it, especially if they're programming in C and other languages where they want speed. It's pretty fast to look at bits inside of the machine, so keep that in mind. Now we know how to do an OR operation, and we know one reason that it might be useful. And yeah, okay, I'm going to move on to the next operation. So clearing the screen now. Hello, little doggy. He barked, and now he's in the room. Let's do the logical AND operation. Okay, so suppose we have 2 bits here. The AND operation will result in a 1 only if both of the input bits are a 1. Whoops, I accidentally cleared the whole entire thing. Let me figure out where my red pen is. Okay. And, okay. So if we have a 0 and a 0, the result is 0, because neither of those are a 1. If we have a 0 and a 1, the result is still going to be 0, because we need both bits to be a 1 to result in a 1. So then that means the 1 and a 0 input bit, not L, 1, would also result in a 0. So you get a bunch of zeros until finally you have an input pattern that is just 2 1s, and then finally the result is 1. So that's a logical AND. Let me do a quick example so we can AND a bunch of bits together. I'm just going to do more random bit patterns. So there's another L there. I'm cringing. I'm self-cringing. 1, 2, 3, 4, 1, 2, 3, 4. Okay. So then I'll do like another 1 there and like a 0 there and a 0. Maybe a couple of 1s. Maybe 3 1s and then a 0 and then a 1, I guess. And we'll just say that we're going to AND those together. So AND... Oh man, I'm mixing uppercase and lowercase like crazy. So to AND them together, that bit position right here, that's going to be a 1. And then we have a 0 because they don't match. They're not both 1. And then we have another 0. And then we have a 1. And then we have a 0 and a 0 and a 0 and a 1. So this is a logical AND. You can use logical ands for a wide variety of things, but one thing you can kind of do somewhat easily is to use one number as a mask against another number. For example, notice how, suppose this was the input number. Let's just say we have the input number up top. And maybe you wanted to make sure that only certain bits were turned on, maybe because you're checking for those bits individually, or maybe you want to just prevent the input from having certain bits on for some other reason. Well, you can apply the mask as the second bit and use a logical AND. I'll say mask here. Sorry, you can apply a mask as the second bit pattern. And notice how in the answer, there are only ones where both, the input and the mask pattern had ones, which means if I wanted to just control only which ones are allowed, I can use the mask. Notice how the mask has ones in these positions. And there are definitely no zeros. There are definitely no ones in any position where a mask had a zero. So the mask can kind of like, mute or mask or control the input pattern. If that makes sense, hopefully. Another thing we could do if we wanted to just check to see if one bit exists, let me go ahead and clear this real fast. I'm going to just do maybe 4 bits this time. So we could obviously do an AND against 4 zeros, and this would result in just, a resulting pattern of 0. So this is not super useful. The result will just definitely be 4 zeros. But notice again how the second pattern is sort of controlling what's allowed to go through from the first pattern. Suppose I wanted to check to see if that particular bit was on or off. All I have to do is mask it with a 1 in the correct pattern. So, the second bit that I just wrote down on the bottom row, I just want to see if that second bit is on or off in the input pattern. I don't care about any of the other bits. That means the result will be this. So now it's much more easy for me to see if that bit is on. I could just compare the value of those bits to a regular integer. Like, for example, if we considered that this was the 1 and this was the 2 and this was the 4, 4 and then the 8, I could just ask now if the final value equals 2. And then I would know if that bit was on or not in the original pattern. And so if I wanted to check to see if this other bit was on, I can move this over here and set that back to a 0. So the resulting pattern would be zeros. Then I'd ask myself, is the resulting value equal to 4? No, it's equal to 0. And so then I could know definitely that bit was on or off. Another thing you can do that I'm going to talk about in a future video is just sort of shift the bits over. You could, instead of checking to see if the value was a 4 or like a direct integer, you could just sort of shift over a certain number of spots and then check to see if it was equal to 1 or 0. Let me put this 1 back over into its original position, just so that we'll have something that had a 1. So if I have 0, 0, 1, 0, if I know that the bit that I'm checking for is 1 from the right side, if it's 1 to the left from the right side, then I could just shift all the bits 1 to the right and end up with a pattern that is 0, 0, 0, 1. I'm not going to talk about bit shifting operations in this video, but just know that you can, and you'll see more of it in a future video. So then, this is another way to check to see if a bit was on. First, you do a mask for that bit, and then you shift bits, and then you just check to see if the final value is a 0 or a 1, which may or may not feel easier than checking for an actual integer in your program. Okay, so we've done OR and also AND. The next bit pattern is called a NOT, which is really easy. It's literally just an inversion of the original bit pattern. So for the NOT, we don't really take 2 bits against each other. We just take an input bit and we just invert it. We'll just say a 0 becomes a 1 and a 1 becomes a 0. So that's a NOT. Pretty easy. We could also NOT, a random bit pattern with L's. So I swear, somebody's going to show up, and this is their first computer science video, and they're going to go tell their parents, hey, there's L's in computer science. So sorry. I'm so sorry. Okay, so I got 4 there. So if I NOT those, then that's pretty easy. It's just going to be the opposite, an inversion. 1, 0, 1, 0. Let me just double check that I did that correctly. Yeah, so that's the NOT pattern. No big deal, pretty easy. So then maybe the next thing that we can talk about is the NOR, which just means not or. So let me draw that out real fast just to show you what I'm talking about. So if we do NOR, Pretty much you can imagine first taking the OR and then NOTing it, so inverting the OR. So for example, if we have 2 bits here, actually let me do a sequential counter, because I think that's more fun. I'm counting right now from 1 to 3, or actually, did I do that in the last one? I started with 0, I hope. Let's count from 0 to 3. So 0, and then 1, and then 2, and then 3. So I'm counting in binary. So if we have 2 input bits and we're going to do a NOR, then the first thing we probably want to do is take the OR operator. So that would be a 0 here. I'll just put OR in parentheses just to let you know that this is kind of a nice first step. You could memorize NOR if you wanted to, but I don't really remember how to do it without doing these steps. So it's going to be 1s for everything else, because in the OR you get a 1 if either of those is a 1. And then the next step is you NOT the OR. I'll just put NOR here just to let you know that you're well, I don't know. If I put NOR, then it kind of sounds like I'm NORing that 1 bit, doesn't it? So maybe here I'll say NOT, just to let you know that this is just 1 step against the previous bit. So the NOT is just going to be in inversion. And so the NOR of 0, 0 is 1, the NOR of 0, 1 is 0, the NOR of 1, 0 is 0, the NOR of 1, 1 is 0. And that's how you do a NOR. And all of these logical or bitwise operators can be used in circuits and circuit design and just, other types of logical operations. I'm going to move on. Let's see, the next one is going to be XOR that I wanted to talk about in this video. So what is XOR? It just means exclusive OR. So it's a little bit more complicated than OR. This is actually a fun one because it has a history with neural networks. When you have a neural network that does not have more than one, or sorry, if you have a neural network that does not have any hidden layers, like if you just have an input layer and an output layer, then the neural network should actually not be able to solve XOR. It should not be able to learn it. You have to increase the topology of the neural network in some way, make it a little bit more complicated. For example, adding a middle layer, one or more middle layers between the input and the output layers. If you understand neural networks, it's just kind of fun to know, oh, XOR stumps a shallow network, and kind of starts to prove that deep networks might be a little bit smarter, or deepish at least. Okay, so XOR, let's start off by counting here. I'm going to do 0 and 0, and then this is the number 1, and this is the number 2, and this is the number 3. And exclusive OR just basically means an OR, but if both of the bits are 1, then it's a 0. So that means either of the bits can be a 1 to produce a 1, but it must be exclusive. The bit that is a 1 can't also be next to another bit that's a 1. So let me show you. So in a double 0, the answer is just going to be a 0. In a 0 and 1, the answer is going to be a 1. In a 1, 0, the answer is going to be a 1. And when we have 2 1s, it's not exclusive. The 1 is, it has a buddy or a partner. It's not an exclusive 1. So we'll say that that's a 0. So that's the XOR. I don't know, you could put like a NOT on top of that, or an AND on top of that, or whatever you wanted to do. And we can make stuff that's a lot more complicated. But these are the basics of OR, AND, NOT, XOR, and NOR as bitwise operators. So thank you for watching this video. That's all I have to say for now. See you in the next one. Hope you learned a little bit and had a little bit of fun. I'm out. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.